In today's topic, we are going to discuss about the analysis and characterization of LTI system using Laplace transform. It states that actually in this characterization of LTI system we have already done in the LTI system unit 2 topic, and in this let's suppose the input is xt and output is yt, and the system behavior represented by the ht in time domain. Okay, then if xt is applied to the system, then out yt is nothing but the xt convolved with ht. This thing is already discussed in the LTI system, but in case of Laplace transform from the Laplace property, if xx Laplace transform of xt is applied to the system, then output become xx multiplied with hs. It means this integral become the multiplication here, and the transform function, which is nothing but the Laplace transform of output with the Laplace transform of input, and in this the transfer function hs is nothing but yx upon xs. As we discussed earlier in the LTI system, this transfer function may be related like that, means the input and output is nothing but related with the differential equation. Okay, this means input the output is look like the summation of k ak, some constant, with differentiation dk upon dtk yt. Therefore the same case the output is also the summation of k moving from 0 to m and bk, and differentiation of dk dtk xt. If we take Laplace transform both sided, then it become the same system, but the xt become xx, and we know the property that if we differentiate any system with one time and take Laplace, then just only single s is multiplied. Okay, and in this system the differentiation is k time. Okay, the differentiation is k time, therefore the s is multiplied with k time. Same case in the output, in input. Therefore the transfer function hs become ys divided by sk, and it is nothing but the output which is the summation of k moving from k to the n ak sk divided by summation k naught moving from k to n bk sk. Okay, let's consider some example. Let's suppose the input signal, let's suppose the input is applied to the system LTI and it is the output, and this if input is applied to the system, then output is this, and this is look like the differential equation. It means in the question is given like that. Okay, and here we are discussing with the bilateral Laplace transform. There has some difference between bilateral and unilateral. We will discuss later. But in this concept, if we take Laplace on both sides, and we know that if differentiation is 2 times, then it just multiply with s square. If differentiate with 1 time, then it is multiply with s. If no differentiation, it just yt become yx. Same case here, xx and bx. Just in this, just common the portion of yx to the system, then the system become ys multiplied with as square, a1x and a naught. Similarly, input side the xx, b1x and b naught. If we common and take for the Laplace for the transfer function hs is equal to output upon input, it become to form the ratio, then it become y1x divided by this portion. b1x plus b2 divided by this portion, which is nothing but the a2 x2 square plus a1x in plus a naught. Okay, in the next question we are going next topic we are going to discuss about the impulse response and the step response. We have discussed earlier that the impulse response is nothing but the response of the system when the input is impulse signal, and it represent with the ht, or in Laplace transform it represent with the hs. Therefore, if input xt and del t or impulse signal is applied to the system, then output yt is nothing but the del t convolved with ht, or it is also represent like that in Laplace transform. This convolution become multiplication. Okay, the Laplace transform of del t is nothing but the 1, and Laplace transform of ht nothing but the hs. Therefore, the impulse response in Laplace transform yx is equal to sx. Okay, therefore in time domain impulse response represent with the ht, and in the frequency domain or in the Laplace transform it is represented with hs. Okay, next topic is step response, st. Step response, we have already discussed that if input is step signal and applied to the system, then output which we get is known as impulse response, in step response. Therefore, this step response is nothing but the convolution of impulse response or the system behavior and input is here ut, step signal. And if we convolve this and open the bracket formulate this, then it becomes integral minus infinite to del h tau ut minus t naught, and it change the limit of the signal. Then limit become minus infinite to ht. Therefore, in time domain we have already discussed that the impulse response step response nothing but the integral from minus infinite to t h tau d tau. But in case of Laplace transform, we know that if we take Laplace transform on the both sides, then st become sx, and in this integral become 1 by s, and this h tau become hs. This means this step response is nothing but the impulse response of the system, Laplace transform of the step response in Laplace transform is nothing but the Laplace transform of impulse response divided by frequency s. Okay, and if we have a step response and we have to find the impulse response, then take just reverse action, and then impulse response is then impulse response is the same is nothing but the signal s multiplied with step response. Okay, the next topic is causality of the system. We have already discussed this topic in LTI system, and in that the system is known, LTI system is known as the causal system if the signal or the system defined only for the t greater than 0, and it is 0 when t is less than 0. It means if t this ht is defined define 0 when t is less than 0, and it should be on the right sided, or means it is any value when t is greater than 0. It means the signal here is right sided signal, and we know that from the property of ROC, if the signal is right sided, then if the signal is right sided, then their ROC is also right sided. And we got one conclusion here that from the ROC we will find the causality of the system if the ROC is right sided. Okay, if the ROC associated with the sensitive function for the causal system is right sided. Okay, if the ROC is right sided, then the system is causal system. And in opposite case, for the anti causal system, the ROC is associated at left sided. Okay, but however both causal and anti causal converge this statement is not necessary. It means the opposite behavior is not possible here. It means if the ROC is if ROC is right sided, it definitely means the system is causal. But in opposite point of view, that if the system is causal, it doesn't mean the system have always right sided ROC. Okay, we will discuss in the question section. Next topic is stability of the system. Stability of the system, we have discussed that the system is LTI system is stable when this integral is less than infinite or converge, okay, or absolutely integrable. Okay, this is absolutely integrable. It means the system is absolutely integrable. It means the Fourier transform of this system is exist. The Fourier transform of the system is exist. It means this lie on imaginary axis, because the Fourier transform is defined for the imaginary axis. If the system lies on imaginary axis, from the Laplace transform ROC, we will clearly notice that if any ROC include the imaginary axis, it is definitely a stable system. Okay, for the causal system, it is said that the ROC should have the right sided, and for the anti-causal, ROC should have the left sided, and for the stability, ROC included the imaginary axis. We will discuss one question here. Now our question is find the transfer function of the system if the transfer function of system Hs is equal to 2 upon s plus 3 plus 1 upon s minus 2, and determine whether the system is stable and causal, and also state that whether the system will stable and causal simultaneously. Okay, let's discuss first point, if the system is stable or not. Okay, for the stability, the system should have a ROC which include the imaginary axis. Okay, if we look into the system, then these have two pole, one pole at s is equal to minus 3 and another pole s is equal to 2. And if we plot in the imaginary in S plane, if we plot into S plane, we got that it include imaginary axis only when the system look like this and this, mean the ROC should in between minus 3 to 2. Okay, it is also possible if we draw another possibility, means if we plot one option like that, consider less than minus 2, but in ROC property we know that ROC must not contain any pole. If the ROC is less than 2, then it contains minus 3 and it is not possible, then it is wrong. Okay, and if the another possibility, if right sided, then if we consider from this side, then it also contain the the next pole 2 is also in between the ROC. This is not possible. Then only one section is possible, that greater than 2, but it does not include this section, therefore it is also not a stable system. Therefore for the stability of the system, it has only one possible, that the sigma should be between minus 3 to 2. Okay, if the ROC of the system between minus 3 to 2, then system is known as a stable system. This is one condition. Okay, similarly we have discussed here, actually we state that the system should have between this, therefore for this ROC between this signal minus 3 and 2 in between, therefore first case the sigma should be greater than minus 3, and in second case sigma should less than 2. then this is a left-sided signal and this is the right-sided signal, and take accordingly the inverse for Laplace transform, and it becomes 2 into e to the power minus 3t ut, and for the right-sided signal, and for the left-sided minus e to the power 2t u minus t. This is the stability of the system. For causal system, it states that when the ROC is right-sided, then only system is causal. For the right-sided, the only one possible is that the ROC should be greater than 2. If we consider one possible like left-sided, that look like that, then ROC is not possible. Then causal system not possible, because for the causal system, it should have the right-sided. Then, if we consider right-sided like this, for sigma greater than 3, it is also not possible because it contains the 2 in between the ROC. Then only one possibility remain, which is sigma is greater than 2. If sigma is greater than 2, it automatically means that the sigma is also greater than minus 3. The combination of these become the sigma is greater than 2, because both the signal is right-sided, then we choose ROC, which is leftmost pole. Okay, then this signal is also right-sided, this signal is also right-sided. Take accordingly Laplace inverse Laplace transform, and we get this possible. Okay, and for the system to be stable and causal both, it look like that the system should be right-sided and it contain imaginary axis also, but combination of both is not possible. Therefore, the given system cannot be stable and causal simultaneously. Okay, it is enough for today's lecture. We will discuss unilateral Laplace transform in next section.